Hello, we have discussed a lot about macromolecular nature and its complicated behavior based on the giant molecule that it is. Over and above, the tunability aspect of macromolecular system is what leads so many applications based on it. And therefore, we are discussing polymer materials of different kinds. And in the last lecture, we looked at the blends and their definitions. And so in this lecture, we will try to look at some of the properties associated with blends and mainly the thermodynamics of mixing. So therefore, we will begin by looking at thermodynamic aspects of looking at free energy of mixing for blend systems and understanding the basic Flory-Huggins theory, which is proposed for understanding the miscibility of two polymer systems. And then finally, we will end with looking at critical temperatures which are present, which demarcate the boundary between miscible and partial miscible and immiscible regions in a polymeric blend systems. Some of these are also similar to small molecular systems. So from a thermodynamic point of view, the theories are very similar. Depending on the nature of molecules and the interactions, the details. So what constitutes, for example, the energy, internal energy of interaction or enthalpy of interaction between molecules may change from one system to the other. Similarly, the entropy of mixing may change depending on the type of molecule we have, because the arrangement of the molecule, for example, in case of macromolecule, we have a very large molecule. So the way different monomers will organize themselves with the constraint of covalent bond between different monomers is different compared to if all these monomers were separate objects. So therefore, the details regarding the entropy and enthalpy of mixing will differ for polymers compared to small molecules. However, the broad framework of analysis of thermodynamics remains largely similar. So for example, ideal gas mixing is something which we have seen from various physical chemistry and chemical physics courses, where the entropy of mixing is basically given by the mole fraction of A and B. And if you notice this, this is a negative quantity, and since this is a fraction, mole fraction, this is less than 1, and so logarithmic of mole fractions will be negatives, and so therefore entropy of mixing will always be positive. And so we know that ideal gases will always mix with each other. And the other hand, the free energy of mixing is always negative because both of these quantities are individually negative, and therefore ideal gases are always miscible with each other. Now, this kind of a problem can be looked at as a problem of probability and combinatorics. So you have two objects, A and B. So let's say we could think in terms of two balls. So if we have, let's say, ball A, and then we have ball B, and we have some numbers of them. So in this case, for example, NA and NB are the numbers of these balls. And then what we have is this is called lattice theory. So we have certain slots, and then we could put each of these balls in each of these slots. So now basically the total number of such slots available, of course, are, let's say, NA plus NB. So this is the total number of slots, and NA and NB is the number of individual molecules of A and B. So then what is different number of ways in which we can distribute these objects in these slots? So it's a problem of combinatorics, and the answer to this delta S comes from analysis. We basically get a binomial distribution, and if NA and NB is large, then we can show that it will be a Gaussian distribution based on which we can then find what is delta S. So generally, this is only valid for ideal gases where A and B don't interact with each other. So they are they can both occupy slots which are same. Also, if there is an A molecule, the probability of B being next to it is the same as probability of A being next to it. So therefore, in this case, the probability of observing A or B on any slot is equally there. But if, let's say, B likes to interact more with B and A likes to interact more with A, then what will happen is, in that case, it is more likely that a neighbor of B is likely to be B. So this is a situation where there is interaction. And so in that case, the overall Gibbs free energy of change has the entropic contribution, and it also has an enthalpic contribution or internal energy of interactions. So this is the enthalpic contribution. And this gamma m is a parameter which tells us how much is the interaction. If gamma m is 0, this is a simple model called Margulis model of non-ideal mixing between A and B. And so those of you who have done activity studies earlier will be quickly able to see that activity coefficient for such non-ideal systems are related to the compositions and this parameter gamma m. If gamma m is 0, then we have an ideal system. The other thing to notice here is if gamma m is negative or positive. If gamma m is negative, then what happens is delta G will always be negative, because the term related to entropy is anyway negative. So if gamma m is negative, overall delta G mix is negative. So clearly systems will be miscible. So gamma m negative implies that A and B interact favorably with each other. So if there is a B, then it's more likely that A will be next to it. And so this is something for us to just ponder about as to why polypropylene and polyethylene form an immiscible blend, given that interactions between them are very similar. And this is something for you to ponder about, because if we have ideal gases where there is not much interaction or similar, so in that case the molecules like to mix. But why is it that in case of polyethylene and polypropylene there is a tendency to form immiscible blends? So we can look at this by looking at the Flory-Huggins expression. Similar to what I talked about in terms of a lattice. So if we have a lattice where there are many slots and there is a molecule A, so there is A, and then there is a covalent bond and A, and then covalent bond and A. So what you can see is, in this case, because of the covalent bond of A and A, there is a chain of A. The neighborhood cannot all be B. One of the neighbor has to be A, because the A chain is continuing. So therefore, if B chain is there, then there is a very limited set of slots which B can occupy, because again there is a constraint of B being bonded to B, and then of course there is a chain of A which is also there. So if you again do statistics of this distribution of how A and B will fit together in such slot, and that is what was done by Flory-Huggins decades ago in terms of the lattice theory, we come up with a very similar expression to what we saw for mixing of ideal gas. So this is the entropic contribution and this is the enthalpic contribution. And just like gamma m we saw, this chi interaction parameter is tells us about interaction between A and B. If this is 0, then we fall back on basically only the entropic contribution. Now, one of the things that you notice is that Na and Nb, these are nothing but degree of polymerization, or it's the length of the macromolecule. And in case of macromolecules, clearly this is a large number. Degree of polymerization or number of repeating units can be in thousands. So therefore, you can see that this term is going to be exceedingly small, because log phi b and log phi a are basically logarithms of volume fractions, and volume fraction can vary between 0 and 1. So therefore, the entropic contribution is extremely minimal in case of mixing of macromolecules. And so any amount of interaction which is not favorable will immediately induce immiscibility in macromolecular system. That's the reason polyethylene, polypropylene are also immiscible. So unless we have on the two chains some molecules which will favorably interact with each other, like we saw in case of polystyrene and polyphenylene oxide, the miscibility is generally not present. So this can be also shown on a plot where we have delta G, the Gibbs free energy of mixing, being plotted as a function of volume fraction of one of the substances, and depending on the Flory-Huggins expression and where the chi is, so chi is a strong function of temperature, and this is understandable because if we change the temperature, we can manipulate the miscibility. Basically, temperature changing is with respect to the interactions between the two macromolecules. And the more the thermal energy is, and the interaction in relation to that thermal energy will determine whether miscibility is present or not. And chi can increase with temperature or decrease with temperature also. So that gives you a hint that polymer mixing may be enhanced when you increase the temperature, or polymer mixing may be actually decreased when you increase the temperature. So in these cases of mixing, when we have delta G of mix for a ideal gas mixture, the behavior is just like this. So this is for ideal gas. So you can see that for all proportions of phi A, delta G is negative. So in case of a polymer blend with partial miscibility also, what you can see is delta G is negative throughout, because this is the zero value. And so delta G is negative throughout, but the shape is interesting. So not only the magnitude of delta G, which is required to be negative for mixing to be spontaneous, but we also need to look at the first derivative and second derivative. So whether there is a maximum or minimum, and also what is the curvature of delta G. And this determines what is the nature of miscibility in the system. So if it is like this, then this is a perfectly miscible system. If the delta G is like this, then this is partial miscible. And we can have a situation where delta G is completely positive. So this is an immiscible system. So therefore, depending on the quantity of chi, we can achieve all of these three, and therefore interaction between polymer A and B determines whether we have a miscible system, partially miscible system, or an immiscible system. So Flory-Huggins theory is a very useful theory to try to understand these different regimes of behavior shown by different polymeric system. And we can analyze this also from the point of stability. So those of you who have learned about the concept of stability based on looking at the curvature, you can understand this, that we can split the overall region into three regions, A, B, and C, where A is the stable region. So that means any mixing of A and B in this region will lead to complete miscibility. But if you have B and C, then there is immiscibility, partial miscibility observed. And B state is fairly important in terms of it's a metastable state, which means if we do not disturb the sample, then it's possible for us to maintain the mixing. But as soon as there is a small fluctuation, and in all real systems, there are always small fluctuations, the partial miscibility will set in, and we will get A-rich and A-lean phase. And of course, in case of C region, we have basically unstable, so we will get phase separation of A-rich and A-lean phases. And so if you see here, what are being denoted are these points. So one which is the basically denotes between A and B, the demarcation. So that's really the boundary of phase separation. So we can plot this information of this diagram. Instead of plotting it with delta G and phi, we could plot it with respect to phi and temperature. So we could plot it with respect to phi and temperature, and this is called the phase diagram in terms of temperature and composition. And generally this is how the phase diagram looks like. So where we are plotting temperature as a function of the phi A, and what we do is all the points which were there on the previous slide, because as soon as you change chi, then delta G will keep on changing, and so we will get different family of these curves. And so for each of them we can denote, for at each and every temperature we can note the phi and construct the phase diagram. And then what we see is in phase diagram we can recognize a region which is completely miscible, Then there is a region where there is partial miscibility, or it's also called miscibility gap. And the phi's phi prime and phi star that we had mentioned, phi star is where there is an inflection point or the curvature changes, and phi a prime is where there was a minimum in Gibbs free energy. So if I prepare a blend here and then start lowering the temperature, basically a miscible blend will go to a partially miscible blend. And so this is the temperature above which miscibility is there no matter what composition I mix. So that's why it's called a critical temperature. And since it's a higher temperature, it's also called an upper critical temperature, which implies that in many polymeric system, you may have a phase diagram which looks like this. So temperature as a function of composition, you will have what is called an LCST, or lower critical solution temperature. So in this case, lower temperature is where there is miscible behavior. And when you increase the temperature, this becomes partially miscible. So polymeric solvent system or two polymeric systems, all these behaviors are possible, that we may have a UCST or LCST alone. It is also possible that we have a combination of both UCST as well as LCST. And what's critical from a polymer application point of view is our target is to achieve a certain set of properties by mixing polymer A and B. And it is of our interest to know how A and B are distributed in the final engineering part that is going out. And this will be depending on how does the phase separation happen. So for example, if I take a polymer sample and cool it suddenly to this, where there is unstable behavior, and we will get what is called spinodal decomposition, where everywhere simultaneously phase separation will happen, and we generally will get a co-continuous phase. Or if I cool the sample to a region where there is metastability, then generally what we get is nucleation and growth. So a few points, the phase separation will start happening and it will grow. So nucleation and growth. So in the end, the final polymer part will have signatures of what was the phase separation mechanism. So this is something which is of great interest from an application point of view. And this is what we will see in the lecture on microstructure in polymeric systems. So let's close this lecture by finally looking at the miscible system itself once more, and looking at how do we estimate the properties. And one important characteristic, as we have already seen, is the glass transition temperature. And since if it's a miscible blend, molecular flexibility of molecule is basically affected by the other molecule. And so if we have glass transition temperatures of A and B, we can have the glass transition temperature of mixture in proportion to whatever volume fractions we are adding. And this is called the Flory-Fox equations. And there are several other empirical relations also available, semi-empirical, theoretical relations, because estimating the segmental mobility of a macromolecular system is of paramount importance from an application point of view. So generally we can add a small molecule and again use similar phenomena. As I have mentioned, miscibility in a and polymer solvent system, the basic framework remains the same. And so what is called a plasticizer, we will again discuss. It's an important additive which is added in many polymeric systems to improve processability and flexibility. So the idea of adding polymers and then estimating properties is very standard. And so for example, in this question, the TG of two polymers, pure polymers, is given. And then it's mentioned that it's a miscible blend and it contains 30% of A. So then what is the glass transition temperature? So therefore, we can use equations of Fox-Flory or other equations to try to estimate this. And so I'll leave you to do the algebra and do the calculations. And so with this, we've come to close on the discussions of the blend. And now with the lecture 30, we will look at microstructure in many of the polymeric systems. And finally, we will have a lecture on composites. So these are all our survey of polymeric materials of different kinds. Thank you.